So we're in the last week of this entire course, and usually in the last week, I want to do something on the lighter side, so you don't need to get too stressed out by the material. There are two topics I actually wanted to do. One is on the induced representation continuing on the Follens book, but I realized that will probably take more than a week to even get to the basic setups. So I decided to do something on the lighter side on these semi-group analysis on semi-group and their C-star algebras. Right, so this is going to be, I hope this is a fun introduction to this topic, and I hope you enjoyed it this week. And why I picked this topic is also related is this the analysis on semi-group. Well, initially people think, well, a semi-group just looks like a group without the inverse, so it should really relate it to how we do analysis on groups. But eventually people realize the semi-group theory is much more different, and all the technique we use is quite different from what happens in the groups. And I'm hoping to give you a basic idea. And the analysis on group is really classical in the sense it dates back to the 60s, the 70s, and the theory on semigroup, the C-star semigroup C-star algebra, really dates back to the early 1990s, actually due to the paper by our very own Andunika. And so it has some association with Waterloo, so I think that's a nice topic to introduce to you. All right. So that's what I'm hoping to do, and I hope you really have a relaxing week and enjoy this week's topic. All right, so let me just give some basic background on the semigroup first. So semigroup is essentially just a set with associative multiplication. It doesn't really need to have a unit, but we usually do assume there's a unit. Okay, so basically, let's just write a unit. It's essentially just E inside P, so that I have E times X equals to X times E equals to X. That's for all X inside P. All right, so this is just a definition of a unit. Usually a unitary semigroup. That's when I say a semigroup, I usually assume a unit, but in the literature, it's often has a special name. It's called a monoid. Okay, so if you see a monoid, it's just a unitary semigroup. But when I say semigroup, I usually assume it does have a unit. And our semigroup doesn't even need to embed inside a group. Okay, but so let's say there's some really nice property we do want the semigroup to have is that first of all is this definition called the left cancellative. So we say P is left cancellative if the following thing happens. So essentially, this allows you to cancel things on the right. Okay, so remember, you don't have an inverse in the semigroup, so you can just multiply the inverse on the left to cancel all things. So you need these kind of definitions. So whenever you have xy equals to xz, okay, then you can cancel out on the left. So it just means y is equal to z. Okay. And similarly, you can define the right cancellation, so right cancellative. If you can do the same on the right, so for every yx equal to zx, you have y equals to z, okay? And if it's both left and right cancellative, we call it cancellative, okay? So cancellative, if left and right, so plus right, cancellative, all right? So that's just essentially allows you to cancel things on left and right, all right? So clearly, if your semigroup is inside some group, so if G is a group, and if your semigroup just embed inside a group injectively, then clearly you will be cancellative because group is cancellative. Okay, so we have P is cancellative. But the converse is actually false. Okay, so they are cancellative semigroup that doesn't embed inside any group. Okay, so it's false. The most analysis these days are focusing on these class of left cancellative semigroups. Okay, so usual sometimes we'll assume inside embed inside group. That's the usual assumption. And another thing about semigroup is we also often in time we don't assume that they have inverse at all. Okay, so another assumption is that so we also often assume that the only invertible thing inside your semigroup is just equals to the identity. Okay, so let's pretend this P is sitting inside some group, so we can talk about this P inverse. Okay, so the only thing in there is just the identity. Okay, so it's really just a cone inside a group, and when you take the inverse, the only thing that's invertible is the identity. Okay, the reason being is really just if there is a lot of invertible things in the semigroup, the analysis on the semigroup really just breaks down into analysis on that invertible part, which is everything that can be inverted, and the actual semigroup part. Okay, so you kind of go back to analysis on the group. So that's it's really just we know how to analyze the group. So oftentimes we can coach in and out and we can study the semigroup anyways. That's why most of the time we have this assumption. All right, so let's just clarify our assumption after all. So throughout this section, so our assumption is that P is a unital semigroup, and P is embedded inside some group, so it's both left and right cancellative, and moreover, P intersect P inverse equals to the identity. Okay, so that's always the assumption. And if you ask about topology, well, there are some study on topological semigroups, but most of the time when we talk about semigroup, we assume it's discrete. So let's just put discrete topology on there, so we don't need to worry about any topology stuff. All right, so let's first compare the major difference between semigroup and group is that it's representation actually. So let's briefly talk about these representations. So for groups, if you think about what happens to groups, so if you want to represent your group using operators, essentially you want a homomorphism from your group, which has a multiplicative structure, to some B of H, which also basically a bunch of operators and also have a multiplication structure. So you want it to be a homomorphism, okay? So by a homomorphism is really just sometimes we call it representation of your G on some B of H. All right, and for the homomorphism, you really want the identity to be equals to the identity. Okay, that's fairly clear. And whenever you have a homomorphism, you don't want your homomorphism to be unbounded. So you want to have some uniform bound. Okay, so if you usually want the supremum of your pi of g is less than infinity, so it's not you're not representing your elements in G by something that's almost unbounded. Okay, that you want to have some control over this norm. And because of that, and so all of these assumptions, if you put it together, that will just imply that your pi of G must be unitary. Okay, so because your things need to have an inverse, and because pi G and pi inverse, pi G inverse, they're inverse of each other, and then because they multiply to the identity. And when you put a sup on their norm, it just shows that they have to be unitary. Okay, so all of this have norm 1, and they're unitary. This is, let me just write it because pi G is invertible. Okay, so you have an inverse. And what happens when you go to semigroup is that you no longer have this inverse. Okay, so for semigroups, you no longer have inverse. So whenever you have say a representation of your semigroup to some P of H, so that's a homomorphism. But because there's no inverse, your pi only have a pi of pq is equal to pi p pi q. That's the only thing you have, and usually you do assume that the pi of e is the identity, but that's basically it. You cannot say, well, it has to be unitary because it may not have a left inverse at all. So what happens is that oftentimes we only have if we want to have some kind of uniform bound, usually we only assume that pi of p less than equal to 1. So it's, in other words, a contractive representation of your semigroup. Okay, so you oftentimes you have contractive. But contractions are really hard to study, especially when you consider their stars, their adjoints, they don't multiply very well. So instead of contractor representations, usually we consider a slightly better one. Basically, one thing less than the unitary is basically the isometric representation. So let's just recall an operator. So V inside B of H is called a isometry. If it preserve the length, okay, so VH is equals to H, that's for all H inside H, and equivalently, because everything is on Hilbert space, this is just implies that if you take a V star of V, okay, and you apply to H, that will always give you the H, okay, so in other words, the V star V is the identity operator, okay, so let me just write V star V is equal to the identity, okay? So for semigroups, usually we don't consider their unitary representation, we consider isometric one, okay? So usually we consider isometric representation of semigroup, okay? So instead of unitaries, okay? So isometric representations, they may not be invertible because its range may not be the entire space. In fact, if you for every v, if you have an isometry, this VV star is basically a orthogonal projection onto its range. Okay, so that's an orthogonal projection onto the range of V. We're going to use that a lot. Okay, so VV star is always, because VV star, if you take it as a P, then P times P is equal to P itself, and then P adjoint is equal to P as well. So that's a orthogonal projection. Okay, so in other words, if you let P is equal to VV star, then P squared is equal to P star. Okay, so whenever you have something like that, you call it a orthogonal projection. Okay. All right, so basically now we let's show some examples. So if you consider what happens in for one thing, okay, so if you just consider the easiest semigroup you can have is just really the natural number. So the natural number for me, they always start with 0, so that's the unit, and it's 1, 2, and so on. So you can embed it inside the integers, which is a group. All right, so that's always probably the easiest semigroup you can imagine. And if you think about what happens to an isometric representation, so if you have an isometric representation, so pi from the natural number to some b of h, then clearly your pi of 0 needs to be identity. That's clear. It needs to be unital. But if you take any pi of k, that's just equals to pi of 1 raised to the power k. So the entire representation is just determined by the value at 1. In other words, it's just determined by a single isometry. Okay, so pi is determined by a single isometry. So let's call it V is equal to pi of 1. Okay. So in other words, once you settled on what's the pi of 1, then your pi of k is just equals to V to the k. And this V doesn't have to be a unitary. Okay. So if V is not a unitary, then this is clearly, it doesn't lift to a representation of the integers. All right. So I want to, first of all, let's talk about, there's a nice theorem in operator theory that allows you to decompose these isometry as some part as purely for the semigroup, and another part that's actually unitary representation, basically representation of the integer.